Hi, everybody. Welcome. I'm so glad to get to talk to you today about a subject that is near and dear to my heart, and which actually several subjects which are near and dear to my heart. One being BoxLang itself, and the second being async programming with BoxLang and some of the fabulous new features and options that you have available to you for async programming. So just a quick poll here. How many of you that are listening today have been, uh, are familiar with CFML's async functionality as it stands in the current engines? Maho, you can kind of give me the response on that since I can't see the chat. All right, and the second question, for those of you who are new to BoxLang, there may be some things that we talk about, or new to CFML development and are just getting started with BoxLang. There may be some subjects we talk about today that you might need clarification. So we're going to give some time for Q&A later to talk about some of those things and make sure that we can address any questions that you might have. So Maho, what does it look like as far as our percentage of CFML developers? Most of the
So,
folks?
so some yes, like three yes, two no. Someone asking, do you mean thread?
Okay. Okay. Yep. I do mean thread, and we'll talk about the differences. So we'll get this party started. My name is John Clausen. I'm a senior architect with Ortus Solutions. I live in Grand Rapids, Michigan, and I'm wearing my Sparty hat today because I'm moving my kid into Michigan State tomorrow for the next several years. I have 30 years of software and application development experience. I started out mostly as a hobbyist back in the 90s, and then I left a career in 2004 and have been full time in this business since then. I have CFML experience throughout that, or throughout the last 20 years and 30 years of development before that. Um, there are two truths about async programming. One, it is very powerful, and when you do it right, it can be a game changer for a lot of things that in the past have been bottlenecks for performance and productivity and time. And in many cases, in traditional CFML, have required us to throw lots of resources to be able to support async programming. And we'll talk about why that is. And number two, async programming can be really difficult because anybody who's developed, for example, in a language where a lot of things are async, like JavaScript, you're kind of always trying to manage the state. And so you have to really be aware and keep track of the state and when things complete and with threads, join hands. I see a couple of folks raise their hands. We are going to give some time for questions later, but as soon as we get into some of the demos, we can take some of those specific questions too. Um, so let's talk about traditional CFML's async functionality. Right now, in the traditional CFML engines, you basically have three options. One is CF thread tag. In BoxLang, we call that a component. It's no longer called a tag. And the CF thread has been around a long time. It creates a new platform thread, and we'll talk about what a platform thread is versus other types of threads later. There's also the parallel collection operation. So array map, array each, array filter all have an option to parallelize. And you can also specify a maximum number of threads that you want in those parallel operations. Once again, those are all creating and using platform threads. And then there's run async, which is a future-based API. Basically, it returns a future, and there's methods that you can run on that future to get the results, to handle errors, anything of that nature. So that's been traditional CFML has basically been limited to those three different types of operations that are asynchronous. And when we started the process of developing BoxLang, we wanted to make sure that it was a modern JVM language, and that we used all the capabilities of today's JVM, but also looked at the ways in which async programming was used and how we could make it much more fluent for the language, because we felt this was a very limited set of options for any developers. So in BoxLang, Let's talk about the challenges with traditional CFML first. First of all, everything is platform threaded, and we'll talk about that in a second. We're dependent on machine resources to support high numbers of threads or potentially high numbers of concurrent CPU operations. The APIs, because each of those functions was developed and introduced over a period of time at different points in the life cycle of the CFML engines, the APIs can be confusing, they can be inconsistent. The way that timeout, for example, in a thread, that attribute in a thread tag is handled is completely different than when you're doing a run async operation. You also have a limited number of options which may or may not fit your programming needs. And also, one of the things, and we still deal with this to some degree in BoxLang, is that the scope injection requirements necessary to maintain the context. All of the contexts, application scope, variable scope, all the scopes that you're used to being able to interact to, it's necessary either that you provide those as thread arguments directly, in the case of the tag, or it's necessary for the engines to inject all of those context objects into every thread, which can create unnecessary memory overhead. And the scope objects injected and used into those operations also have to have their own thread safety. So if anybody's used ColdBox and you've ever used the thread safe attribute, component attribute, that's a way that we've tried to actually allow Wirebox to create components that are thread safe. But realistically, mostly the thread safety is determined by the JVM. So those are challenges with async. Now in BoxLang, we've set the goal to have next gen asynchronous programming capabilities, and we built it for today's JVM. There are things that you can do around threading. There are ways that the system uses resources in modern versions of Java, specifically in Java 21, which is the minimum for BoxLang, that that you can't do with any older versions of the JVM. You just don't have those options available to you, which is one of the reasons when we started with BoxLang, we said we're going to use the modern JVM and we're going to start with Java 21, and that's our minimum. And then we'll continue to iterate up and support new features from there. So let's look at BoxLang's async options in comparison to traditional CFML. So we have the thread component, but we've enhanced it, and I'll show you that in a moment. We have parallel collection operations, and we've enhanced those to allow to process more efficiently on the JVM. And later on, I'll talk about the future and some new things we're doing with those. We also have run async, which is future-based. The API is very much similar to what traditional CFML engines have. But in addition to those three kind of standards of what CFML developers are used to expecting, we have a completely new object-oriented programming framework. We have config-based schedulers. We have new tasks and scheduling, built-in functions, and an API that's very fluent and easy to use with those types of with async programming. In addition, we have executor configurations, and executors are very important because they determine how the JVM is actually going to run those threaded operations, and built-in functions to handle, create executors, retrieve them for usage in those functions, and they give you granular control on execution and resource usage. So this is all very, right now there are over a dozen new async functions, built-in functions that have been introduced into the language. And there will probably be more coming soon down the road as we sort of determine where the issues are and where we want to enhance these features. So there's a lot of different async options that we've introduced in BoxLang in addition or on top of the traditional three that we've already enhanced. So let's talk about the types of threads, because this is very important. In my CFML slide, you'll notice that I mentioned that all of the threading that's done, async programming that's done in traditional CFML engines uses platform threads. So what are platform threads? They're your traditional thread, and they are mapping one-to-one with the operating system. So when you create a new thread, the JVM has to acquire that thread. It has to have the processing resources available to obtain that thread. If the maximum number of threads on the machine has been reached, it will have to wait around for acquisition of its thread. But it's one-to-one. You're using processing resources of your machine, the hardware that it's running on directly, or the virtualized hardware. Resource usage. Each platform thread has a significant memory footprint due to its own stack and having to maintain its own stack. So a portion of the heap size that you've allocated goes with that thread and actually becomes part of the thread's memory, taking up and consuming the entire memory footprint of your JVM process, in this case in a CFML engine or BoxLang. Also, creation and switching. Okay, this can be really expensive in terms of time and resources because once again, you have all the overhead required to obtain and create that thread. So that process ideally, if your machine is at idle, it's probably pretty fast. But if your machine is under heavy load, the process of obtaining that thread can be expensive, and I'll show you some examples of that in a little bit. And then in the use cases for platform threading, they're really suitable for like long-running tasks that take a lot of CPU resources, interacting with native code where you need to do heavy processing. So give me some examples in the chat of just ways in which you've used threaded operations in the past, or if you're a CFML developer. For me, a lot of ways have been just downloading content or API responses that I might need. Maybe I need a bunch of different resources that I'm going to go ahead and make an HTTP request for. I'm going to wait around for that request to complete, and then I'm going to return the JSON or XML response that becomes part of the array process later. So for me, that's one example. Maho, are there any other examples that have shown up in the chat?
Not yet. Well, someone said earlier they use threads often in Lucy.
Mm-hmm. Yeah, we'll take a look at the chat and come back to it, and we can talk a little more about that. But a lot of times when I'm using any kind of parallel operation, any kind of CF thread, any kind of platform threads, I'm using them because I'm waiting for something to happen. And I want to speed up all the things that are happening because I don't want to wait around in sequence for a 2-second or a 1.5-second response from an API provider and do that 60 times or 100 times or whatever I need to do. So for me, that's been a traditional use of threading. Also, things like processing images or generating PDFs, reports, things of that nature. Those have all been candidates for async operations. And so platform threads, if we talk about those things that I just mentioned, those things which are expensive from a CPU standpoint might be image processing, right? Resizing images or creating maybe I take one big image that's uploaded and I create a subset of different image sizes that I want to be able to serve up on my site in different parts of in different pages and different sizes. Same thing with PDF generation. It's CPU intensive. But waiting around for an API response that's going to be JSON that I'm just simply going to stick an array and a return is not a CPU intensive task. I'm waiting around for a long time, which then introduces the need and the benefit of virtual threads. So virtual threads were introduced in JDK 19 as an experimental feature. They became permanent as part of the JDK in 21. Now, virtual threads, I am a virtual thread nerd. I've been to a couple of Java conferences and have really paid attention to that technology as it's progressed. And it's become something that's incredibly powerful. And it's one of the things that we've done in BoxLang is made it very easy to use these virtual threads. So what they are is they're multiplexed on top of a small pool of platform threads. They're not directly tied to OS threads, but they basically are self-contained. They're much more lightweight than the platform threads. They allow for a larger number of virtual threads to be created and managed with zero overhead. So the creation and the context switching aren't necessary. That's required with the platform thread, where you have to obtain the physical resources from the machine is not necessary in virtual thread world. It's basically instantaneous. And so you have the ability to create large numbers of threads, thousands, hundreds of thousands, even millions of virtual threads with virtually no additional overhead. So where platform or virtual threads shine is concurrent applications with outbound tasks, reading, writing, like I said, making API requests and then assembling all the body of those API requests into a singular response that you want to return to a client. Those are ideal because so much of the time that we've spent with with our async operations in CFML up to this point has been platform threads waiting around, basically tying up CPU resources for no reason. That at the time it was the only way we could do it, but with virtual threads, we no longer have that necessity. So let's take a look at what that looks like. So this is a traditional thread.bx. This is just a class. And if you're not familiar with BoxLang, I'm going to be running these on the command line today. So in BoxLang, you can create a simple BX class. And if you have a function main, you can go ahead and run that class. So this is a very simple code, but basically all I'm doing is mimicking waiting around and demonstrating what that looks like. So all I'm doing here is I'm starting with 10 iterations. I've got, my thread names. Let me open my chat here real quick. Come on, what is going on with my Zoom bar? There we go. Okay, I'm moving that over here so I can see. Okay. So yeah, looks like most of the folks who have been using threading have been using it kind of in similar ways that I mentioned before. But this is a pretty basic example. Right now, basically, we're taking 10 iterations, and in each iteration, we're going to sleep for 5 seconds. Then we're going to join those threads back together. We're appending our list. Now, this is also another pain point of CFML, right? Or traditional thread operations is the naming and the joining and all that. They have to be separate operations. And at the end, we're just simply going to get a tick count, and we're going to say these operations completed in whatever milliseconds it ends up being between the difference between the end and the start. So if I have one thread and I basically have no other code and I'm sleeping for 5 seconds in each thread, approximately how long would you expect this to be with a traditional thread? Well, ideally, what would it be? Exactly. Paul says 5 seconds. So let's see what that actually works out to. So let's go async all. I'm going to go with thread.bx. Whoops. And I'm going to go ahead and run it, and I'm going to see what that takes. So I did 10 iterations, and I have to wait here for 5 seconds, but you can see it completed in just about 5 seconds. So that's about right. So remember, these are all platform threads. They're competing and acquiring CPU resources. So let's now go ahead and bump that up to 100 and run that again and see what that looks like with 100 iterations on the same thread, sleeping for 5 seconds. So a little bit slower, and that's all the acquisition of the machine resources that it takes. Let's change it and let's try 10,000 and see what that looks like. So now we can see I've exceeded my additional 5 seconds. Now I'm at 9 seconds to sleep for 5 seconds for 10,000 iterations. What do you think that's happened? Why do you think that happened? Dan Card, you were the last one to talk, so I think you've got to venture a guess. Bingo. We are waiting to acquire those threads. So all of the additional 4.5 seconds that we took for this was just simply in acquiring platform threads. Now I can take this to 100,000. I can tell you at 100,000, it takes about 60 seconds for this whole process to complete, because all of a sudden it's requesting those resources furiously and waiting around for them to be there. So what BoxLang did was we introduced the virtual attribute to the thread tag. Now, what that does is it changes the way that those threads execute, and and then processes those for you using those virtual threads. So let's just look at our, if let's just start with, we don't mean to start with 10, but we'll start with our first initial 100 and run it using virtual thread. And we'll wait for 5 seconds. Now, I will say that I do this thread and I run it at 1,000,000, I will get a heap space error. It'll just go completely out of heap space and the whole thread will crash. I was testing how far I could go, but my machine has a fair amount of processing resources, so I have to go to about 1,000,000 sleeps before it actually dies. So now you can see that my 100 iterations compared to, is pretty comparable, a little bit faster. But now let's look at what happens when we go up to our 100,000 of virtual threads. Because there's no acquisition time, I can run that. And there is a little bit of overhead from what BoxLang has to do to provide the context to the thread and things like that. But you can see I just did 100,000 iterations at the same speed approximately that I did 100 iterations. So what that means is that the JVM is not working. It has no time to wait for those threads. And so I can do 1,000,000 threads, 1,000,000 virtual threads, sleeping 5 seconds. And even doing that, let's see what we get. It's going to take a little longer. It's working here. So I'm probably going to have, once again, there is some overhead with the need to inject the context here. And there's obviously, a common pool that has to be established. But I can tell you that at 1,000,000, I bring my machine to a halt with a platform thread. And this one takes 36 seconds for 1,000,000. And it takes, for 100,000 with platform threads, it takes over almost 70 seconds, it's about 68 seconds. So the ideal situation for these platform threads is dealing with things that require you to wait around. Because generally, if you have a reasonable number of iterations, you're going to execute the execution is going to take the time of the longest request, and that's it. You don't have to wait for any time to acquire. You don't have to wait for any time to deal with the JVM or the minimum resources on the machine. Virtual threads are infinite. So question is, John, what is the rate of virtual greater than platform threads? Is it configurable? No. The answer is no, because the JVM manages virtual threads and they're virtually unlimited based on the resources of the current thread being executed. So the only limitation you do have to remember is that while they're not bound to the running request thread, the JVM is using its own pool, and that pool is fixed at the moment. There's never been any kind of configurability. Now with the thread tag, you don't have any ability to configure the pool size either. With the other async operations, which BoxLang has introduced, we actually give you that option. And I'll talk more about that in a moment. So let's go back and look at, come on. Let's go back now that we've talked about traditional threads, which we're familiar with, and talk about some of the new async OOP programming. So we basically we categorize these into 4 sections. We have futures. So an example of this might be future new, do this, do my work, and then do get, which will get, in this case, completed result, which is a string. But if I were waiting around for an API response or whatever, that future would be able to resolve. And the future API has a lot of different options available to you. So that's one of the things that I don't have time in this to cover all these different options. But if you go to the Box Futures page, you're going to see there's a whole lot of different operations that you can use on a future. I can do then async. Oops, sorry, I want the future API. Um, I can create a custom executor. Remember we talked about thread pools? So I can do a custom executor. So I can actually do, in this case, let's just do a second here. It's, and so in this case, I could do, actually my other example would have been there. Um, I could do future new. In my iteration. Notice I used this syntax. So this is a Lambda syntax. What that means is that there is nothing that will run in this function that will use the context or have the context outside of it available. Whereas the double arrow, which is the standard closure you're used to using in CFML, they go ahead and bring in the entire context. So I could use the variable scope or whatever. In this case, I don't need it. So I can do just standard future new get, and then that's my result. Or I could do a custom executor. Now, one of the things we talked about in the executors is that you have that, we'll show you in a moment how those get configured. You have a lot of different configurations, but there are already several executors that are created. Remember how we said that platform threads are best for CPU tasks and virtual threads are best for IO tasks? So what the future gives us the opportunity to do in BoxLang is I can specify which executor I want to use. So in this case, I could go ahead and say IO tasks, and that executor is my virtual executor. That's the built-in virtual executor that BoxLang gives you. Futures are like promises in JS, exactly. Although the API is a little bit different. But yes, Jacob answered that even better than I could. So thank you, Jacob. So future new gives you the option. There's a lot of different functionality, and if you kind of go through, what that looks like, you've got the ability to get it. You can set a timeout on how long you're willing to wait before you get that. You can specify time units in time units specifically. So you can say 5 seconds instead of passing in milliseconds. And then there's also the non-blocking alternative, which you can do the joins on the future. You can do a join, or if you can't join it, there's a failure. This is the default that it returns. So these are all different options that you have with just a single future. Now, with futures, you don't really get, you're not getting like multiple operations in the same way that you can with the parallel computations, but they're incredibly powerful if you need to do something async or do some other work while that's happening, like a promise, like a JavaScript promise, and then come back and get that result and then use it somewhere else in your code. So we oftentimes, if we look at traditional CFML developers, we've often programmed in a blocking way. We've assumed blocking because all of our programming up to the point of CF thread being implemented was all blocking code. And so we do this, we wait for this, then we do this, then we do this, and then we process maybe that thing that we waited around for 100 lines up. But what futures do is they allow you to kick off that processing, fire it off separately, and then go ahead and do other things concurrently, and then come back, grab the result of that future, and then work with it in whatever way you need to do with the response. Very similar to what Java's or to JavaScript's promises. Now, we have had that functionality with run async, but what we didn't have with run async was the option to use different types of executors to handle the work. And so that's where being able to say, like, if I'm going to process an image in this future, I might use the CPU task executor. But in this case, I'm just sleeping around or sleeping and waiting around. So I'm going to do the IO task executor, and I'm going to go ahead and just get that. So if I run that one, we're going to see that should take I don't need a thread action, a join action. Why does So I'm going to go ahead and just wait for that. So let's do, actually, I could have gone with a smaller number of iterations, so I didn't make you wait around for it. Actually, going to just change that to 100. Okay. So now what you can see is that we have the future acquisition that has to happen, and then the executor has to be used and all that. So we are introducing a little higher overhead to get that future. But if I said my timeout on that was 1 second, like let's say I said get 1,000, I'm just going to get everything back in a second. So there's a little additional overhead with the future that you don't have when you're using threads, the virtual threads directly, but that's there. So let's go back and talk a little bit about next async pipelines. So async pipelines are basically just kind of the next generation of async run. They can operate on the futures, just like what you're familiar with. Whoops. Let's go back. Eh, eh. No. Oh, okay. Sorry, guys and gals. All right. That last one is what I wanted to do. Um, so then there's the async pipelines. And so async pipelines are documented here, and you can see there's lots of different options. So I've got async pipelines run. Um, I can use the future syntax, async run syntax, and then you've got all the same methods that you would use would use with the future. And so these are all operating on futures. Then, in addition, then we've got the parallel computations, and there's a lot of different types of parallel computations. So this one I'm going to spend a little time with and demo the same thing that we saw with regular platform threads versus virtual threads. So there's async all apply, async each, or excuse me, async first, and we'll kind of go through what those different methods are. And then the last thing we have, which uh, you know, Lucy and ACF have always had the concept of scheduled tasks. And traditionally, you've got to go and configure them in the admin, and then you have to have a publicly accessible URL that you go ahead and have them request, which required you to then secure that in some way so that someone outside of your scheduled task couldn't hit that URL. And then you would go ahead, and that would just be basically a cron job. It runs this request and then does the processing on a schedule. With the advent of CFconfig, that got a little bit easier because you could put your schedule items into the web context config or into the server config, and then you could go ahead and just once you started your server, those tasks would run. Now, one of the things that was a problem with that is that oftentimes it didn't lend itself very well to a cluster. So you had to have a separate configuration of tasks that would only be on one server, but even if that server was running your main application, and you didn't have a lot of flexibility in how those tasks were managed. So what we did was took some of the goodness of ColdBox's async manager and applied those lessons into BoxLang, which is where all of our parallel computation methods come from. So those parallel computation methods are extremely powerful. You've got async all, async any, okay? So that's going to just return the first result. Async run, which is going to execute the single function, and then all apply. So which is going to apply it, and you provide a mapper so that you take the result and then do something with it. So all these pipelines, these parallel computing pipelines, give you a lot of functionality, and I'm going to give you an example of that in a second. And then the schedule tasks, as we said, you can configure those or you can dynamically create those. So let's look at what that looks like. And show you the same example but using the parallel computation. So this is pretty much exactly the same example as what we had over here in our thread test versus virtual threads. So let's just start at, in this case, we're doing basically 100 iterations. We're appending closure here, and we're doing the same thing, sleeping for 5 seconds. Then we're just tracking how long it takes. So notice here in this, I have the actions, which is the array of things to execute that I pass in. But then, in addition to that, we also have the option to specify the executor. So the CPU tasks executor, for example, let's go to 1,000 so we get some, is going to pretty much, it might be a little more performant because it's using a different type of pool. But let's just do that. So that's our 1,000 iterations. And what was that in? I should have actually put the iterations here. So that was, I think 9 seconds is, no, 10,000 was 9 seconds. So this is a little bit slower. For one, I'm starting to count here, but this is still using the CPU tasks. So I've got the CPU task executor in BoxLang. So let's look at what its default is. Okay. So the CPU tasks has a max thread limit of 20. So once I hit 20, I'm waiting around for this to complete. So I could bump this up. I'm not going to do that right now, but you can see that the executors could be configured. So you could have 100 threads. Whereas when I do regular thread, I'm actually creating I'm directing BoxLang to create a JVM thread at that time. So when I do async all, you can see I'm waiting around. Most likely what I'm waiting around for is for the next thread to become available because I only have 20 available to me. So if I change this to IO tasks, which are unbounded and have no limit, I wait for my 5 seconds and I'm done. So you can see that there's a tremendous difference between the types of executors. And so if we look at the different executors available to you that are out of the box, we've got a cached executor, we've got the virtual executor, which is what we just used. You can create a fixed executor. You can also do what's called a work stealing executor. And what that means is that Java in parallel operations will allow you to use a work stealing executor. And what happens is when some threads are waiting around or they're requiring more significant CPU resources, it will actually steal work from another thread that maybe isn't as active or maybe isn't as intensive, and optimize the execution of all of the threads in the pool through work stealing. And then there's the fork join pool, which is when we're using the CPU tasks or the CPU task executor, we're using the fork join pool executor. And you can do scheduled, you can do single. And so in your boxlang.json, you can configure all of these. You can configure your own executors and reference them in your own async operations. So my custom executor, if I had created that in BoxLang, I could go to my boxlang.json. I could say, I want, oops, I want a new executor. I want custom, and then I want this to be work stealing. I'm gonna get rid of my comment errors. So then I could go ahead and say I want a work stealing executor that has 100 threads in the pool, and you would have to have the resources to do that, or maybe I just can. But this stealing 20 thread executor could be faster than the CPU task executor, depending on what's being executed inside that code, because of the ability to do work stealing instead of the standard fork join pool. So the executors themselves are very powerful, and you can use them in different ways. So then when we look at, so that's kind of just additional async operations. And so like, let's say everything in this, let's go back to this task. Everything in this right now is going to execute every single operation, right? And then in this case, if I wanted to do async sum, for example, so where is it? Just so I'm down here so I can show you. So async sum. Any, that's it. So I'm going to do async any instead here. And then I'm going to do a random range on how long I sleep here. So now I'm going to go ahead. So I'll have a random range here. And you can see that the async all operation, or in this case, it's async any, completed in 1 second, probably because the random one that ran first was completed first, and then it just went ahead and returned the results and didn't run any of the rest. So async any is for when you need to do a bunch of operations, but you only need the result of one of those. And I can't think of any examples off the top of my head, but it's there and it's available in your toolkit if you wanted to use it. So that's parallel operations. And then what's next for BoxLang? So we continue as we've sort of gone down this path. 1.4 introduced all of these async methods like async all apply, all those. What's next in the future, we've continued to talk about. First thing that's going to happen in 1.5, you will have the parallel, or excuse me, you'll have the virtual argument to all of the parallel operations on array, list, struct, each, map, filter, all those operations that you can parallelize currently with member functions or with built-in functions. You're going to have the virtual option. So you'll be able to specify virtual equals true. It will use a virtual thread pool, and it's unlimited. So that one will be next. Async modifiers. So think about JavaScript and the way that we use. And JavaScript's a little weird because in order to be blocking, you have to declare the outer function async, but then you put the await in front of the promise or whatever you want to get to go ahead and block. So JavaScript is a little weird in the way it handles asynchronicity. So the async modifiers will be part of that. So you might have a function where you, this is just proof of concept at this point, where you declare async on the function, and whenever that function's called, it's executed and then returns a promise. So you would still be able to use the same promise API. Coroutines. If anybody has ever been familiar with Go routines, basically, I'll just give you an example here. So Go routines are basically a specific way to direct parallel operations, but have the outer function complete and join all those parallel functions before it returns. So it's the same kind of thing where you're doing like future new and all that, but in this case, creating routines that allow you to do things in parallel operations, but then not block. You can start parallel Go routines in a lot of different ways, and they're super powerful. And we want to take and expand the existing API to make BoxLang the most powerful JVM compiled language for async programming, which I feel at this point we already are, but we're not going to stop there. So that's super, super exciting. So the wrap up, BoxLang offers you a really comprehensive suite of tools to use modern concurrent programming for the JVM. It's built on today's Java APIs, and we're going to leverage the new ones when they become available because Java is not stopping either, and so we're not either. And they're also enhanced with the dynamic language features and developer-friendly APIs, unlike the traditional CFML methods that we've had up to this point. So with that, I would love to take some additional questions. Where's my chat? Did you lock everyone from chatting, Maho?
I might have, let me see. I just got too worried about that.
All right. Well, I'm happy to take some additional
I
questions.
think they can. No, they can. Yeah.
Ramaha, yes, we do. We do offer in-person training. We have lots of different types of training offerings available. So whether your needs are in the existing CFML space or whether you want to learn BoxLang and async programming options in person, yes. And please feel free to contact info@Ortus Solutions, and we can get you all the information you need. I'm sorry, I want to say it right. Is it puck or pook? Either way, the answer is mostly yes. I imagine it seems like the last, as we've announced some of these features that has been duplicated or implemented sometimes in other languages, but at the moment, these options with virtual threads and the executors and the async API, yes. That would be a question for Maho. Does this go on CFcasts?
Yes, it is. So we will have it available on CFcast, also YouTube, and we will share with you as well via email. So you'll have the report. But I'll need to add it. And
Yes, after some editing.
yeah, yeah, of course.
A couple of things I would just wanted to kind of go back and reiterate. There's a lot of different functionality that's been introduced with 1.4. There are so many different ways you can handle with schedulers. Schedulers alone, you've got powerful options. Remember how we talked about the issue with clustering? You've got the on one server option here where you can use a cache, a distributed cache. And run it only on one server and be guaranteed. And you can also configure it so that if you don't want to run it with another, with a space delay between one completing and the next one starting, you have space delay. You have a lot of just fluent options. I want to run this task every day at whatever time, and then with the result, I want to do this. So there's a ton of different options. And so my suggestion would be to go and dig into boxlang.ortusbooks.com, look in the async programming section. You can also look in the reference section if you want to know more about the built-in functions that are available and their method signatures. You can see all of these different functions that we've introduced. Executor functions, is thread alive? Is it interrupted? Is it in thread? The run async, which you've traditionally done. A lot of different, and so like the thread now no longer requires the component even annotation. You can use the methods natively. And then in addition to that, you can kind of browse through there and look at the method signatures. And then for parallel operations, if you want to look at the parallel operations and how those work, you can go ahead and look at the documentation on that. Soon, hopefully in 1.6, you're going to see the virtual option, which will become available. And so what the virtual option is going to be is it's going to be use your virtual executor for those operations. And so you would just provide parallel true and then virtual true. Any additional questions? Pook, yes. Use a lot of Node. Okay. So yes. So basically, yes, the Java code and the JVM compiled languages up to now have been mostly synchronous, and async has been, something that you had to be purposeful about. Whereas anybody who's using Node or JavaScript is used to the opposite, that where you have to force synchronicity. So it does change everything. A lot of the things that you might be used to in working with Node where you're, making API requests or you're downloading assets or whatever, those things you're used to being through the Promises API, used to being async, or in some cases executing out of sequence. Right now, BoxLang and almost all JVM languages really out of the box are designed to be synchronous. So it takes a little while to change that kind of mental picture. Any additional questions I can answer? How threading and locking shared resource can be used optimally. By the way, Pook, I will go ahead and with this set of files, I'll publish this so folks can look at these examples, and I'll try to give you a couple real world examples, like downloading something from an API that's publicly accessible that you can run and test. So threading and locking, the best way you're going to be able to manage those is to manage either the size of the thread pool so that you can control the amount of resources. So if we go back to my example, and I look at my thread example here, this is super dangerous for resources, because if I'm doing anything heavy in this, I'm asking the machine to create 10,000 different threads. Whereas when I ran this through async all and I used the CPU task executor, we saw that's configured by default to 20 maximum. And so I can control the resource usage on that, even though it's going to take me more time to execute the operations by maxing out the number of threads, the number of concurrent resources that can be used, or if appropriate, use IO tasks so that you can use virtual resources, which are completely unlimited. Time for one last question. Going once. Going twice. All right. Thank you all for your time today. It's been a pleasure. And I hope you'll take some time to really dig into the new API programming options you have available for async functionality in BoxLang. And I think you're going to find those virtual threads and the virtual executors like IO tasks are very handy when you start to expand on it. Go ahead, Poop. Since those options are only available, ColdBox doesn't really use threading much on its own. But right now, Luis is in the process of a BoxLang Prime version. And I'm guessing since he'll probably be touching the async service in that, he will use native, probably have some conditionals in there to use native where he can. So ColdBox for a long time to come is going to have to be agnostic, but we're in the process of working on a BoxLang Prime version that can run without CFML compat. And once that happens, then there's the opportunity to use a lot of the native functionality. All right, everybody, thank you so very much. If you have any additional questions, you can always ping me in CFML Slack at jclawson. Or if you're on Box Team, you can ping me there. I'm happy to answer questions individually.